When you see something as amazing as the aurora borealis, or you hear about giant particle accelerators, have you ever wondered what's behind it all? Well, the answer comes down to one fundamental concept in physics: how charged particles move through magnetic fields. So today, we're going to dive into this incredible dance between electricity and magnetism and see how it shapes everything from cosmic events to cutting-edge technology.
So, here's our game plan. We're going to start with the absolute core of this interaction, the fundamental force itself. Then we'll unpack the math for two key trajectories, that perfect circle and the more general helix shape. And finally, we'll see this physics in action, from the massive Van Allen belts all the way down to the kind of problems you'd solve in a lab.
All right, first things first. We have to establish the basic interaction between a moving charge and a magnetic field. And it all comes down to a very specific and very important geometric rule.
Okay, quick refresher on magnetic field lines, what we call the B field. They show the field's direction and strength. And you'll notice they always form closed loops. That's a huge deal, by the way. It's because magnetic monopoles don't exist. It's a key difference from electric fields, which can start and end on charges. But what we really care about today is what happens when a charged particle flies through this field.
Now this is the single most important idea for everything we're about to talk about. The magnetic force always pushes perpendicular to the particle's velocity. And in physics, work is force times distance in the same direction. Since the force is always sideways to the motion, the work done is zero, always. So what does that mean? It means the magnetic field can change a particle's direction, it can steer it, but it can never change its speed or its kinetic energy. It's a pure turning force.
So, let's see what happens when we take that perpendicular force to its logical conclusion. We'll imagine the ideal case, a charged particle zipping into a nice, uniform magnetic field with its velocity perfectly perpendicular to the field lines. This setup leads to a really simple and elegant path. You'll remember, for anything to move in a circle, you need a force that's constantly pulling it toward the center. We call that a centripetal force. If you didn't have it, the object would just fly off in a straight line, right?
And here's the beautiful part. In our case, the magnetic force is the centripetal force. Just look at the diagram. As that particle moves, the magnetic force, those red arrows, is always constantly pointing right to the center of the circle. That relentless inward pull is what keeps deflecting the particle, bending its path into a perfect circle. So now we get to turn this physical idea into an equation. It's as simple as this. We just set the formula for the magnetic force, which is QVB, equal to the formula for centripetal force, mv squared over r. This one little equation is the key to connecting everything, the particle's properties like charge and mass, its speed, and the size of its circular path.
Let's just walk through the algebra real quick. We start with QVB equals mv squared over r. We can cancel out one of the v's on each side, which leaves us with QB equals mv over r. Then just rearrange it to solve for the radius, r, and there you have it, r equals mv over qb. This is such a useful equation. It tells you that the bigger the particle's momentum, mv, the bigger the circle. And the stronger the charge or the magnetic field, the tighter the circle.
But wait, it gets even cooler. We can also figure out the period, t, the time it takes to do one full lap. You just take the circumference, 2 pi r, and divide it by the speed, v. Now watch what happens when we plug in our new expression for r. The velocity and radius terms completely cancel out. And we're left with this really amazing result. The time it takes to go around doesn't depend on how fast the particle is going or how big the circle is. It only depends on the particle's mass-to-charge ratio and the strength of the field. This is the exact principle that makes cyclotrons work.
Okay, so circles are great, but that was the ideal case. What happens in the real world when a particle's velocity isn't perfectly perpendicular to the field? What if it comes in at some random angle? Well, the trick, as it so often is in physics, is to break the velocity down into components. We'll split the velocity vector into one piece that's perpendicular to the B field and another piece that's parallel to it. Then we could just look at what happens to each piece on its own. And this slide just shows it perfectly. That perpendicular part of the velocity, it interacts with the B field and creates the circular motion, just like we saw before. But the parallel component is moving right along the field lines. The magnetic force has no effect on it at all. So that component just keeps moving in a straight line, completely unaffected. When you put those two motions together, a circle and a straight line, you get this beautiful corkscrew shape, a helix. And we can actually quantify how far the particle drifts forward with each loop. We call that distance the pitch.
You just calculate it by multiplying that parallel component of the velocity by the period, t, which we already figured out earlier. All right, enough with the equations for a minute. Let's go see this helical motion playing out on a planetary scale. This is where all this theory becomes a real, visible, and pretty awe-inspiring thing.
So, the Earth's magnetic field acts like this giant invisible shield, protecting us from a lot of the charged particles streaming from the sun. But some of those particles actually get trapped by the field, forming these huge donut-shaped regions called the Van Allen radiation belts. The particles inside these belts are just spiraling back and forth along the magnetic field lines, bouncing between the poles. It's like they're caught in a magnetic bottle.
And near the poles, where those magnetic field lines dip down into the atmosphere, some of those spiraling trapped particles can actually crash into oxygen and nitrogen atoms. These collisions get the atmospheric gases all excited, and they release that energy as light. And that right there is the aurora. It's literally just particle physics lighting up the night sky.
Okay, so let's bring it all back down to Earth, back to the lab, and apply these ideas to solve a couple of problems. This is how we can actually engineer these fields to control particles.
Here's a super typical scenario. We've got a beam of alpha particles, which are just positively charged helium nuclei, and we need to use a magnetic field to bend that beam around a 90-degree corner.
So to find the field's direction, we just pull out the good old right-hand rule. For our alpha particle coming from the bottom, the velocity, v, is pointing up. We need the force, F, to pull it to the left to make that turn. So if you point the fingers of your right hand up and your thumb to the left, which way does your palm face? It pushes into the page, and that's the direction our B field needs to point. Now for part B, we need the transit time. First, we use our period formula, T equals 2 pi m over QB, to find out how long a full circle would take. We just plug in the numbers for an alpha particle and the given field strength. But we're not going in a full circle, right? We're only going 90 degrees, which is 1/4 of a circle. So the time we're looking for is just that total period, T, divided by 4.
The final calculation gives us about 33 nanoseconds. That's 33 billionths of a second. It's just incredibly fast, and it really shows you how effective magnetic fields are for precisely controlling where charged particles go. It's the foundation for things like particle accelerators and mass spectrometers.
Okay, let's look at a slightly more complex problem. Say we have a proton entering a field at some angle, and we want to find the exact angle where the pitch of its helix is equal to its radius. Well, all we have to do is set our equation for pitch equal to our equation for radius. So v parallel times the period equals m times v perpendicular over qb. We can substitute in our trig components, v cos theta for parallel, v sine theta for perpendicular, and our formula for the period. And what's really neat is that after a little algebra, the mass, charge, B field, and even the initial speed all cancel out. We're just left with a simple trig identity we can solve for the angle, which turns out to be 77.9 degrees.
So as we've seen, this whole interaction isn't just some abstract concept. It's a really powerful tool. It lets us bend, guide, trap, and even sort particles based on their properties. Which leads to a final question for you to think about. Besides the stuff we've talked about, what other major scientific instruments, from the chemistry lab to giant physics experiments, are completely reliant on this one fundamental principle?